Hi, my name is Matteo, and this is the presentation of our paper Tracking Skiers from the Top to the Bottom. This is a joint effort between myself, Luca Sordi, Niki Martinel, and Micheloni. We work at the University of Udine, Italy. Skiing is a globally recognized and highly popular winter sport discipline. Its competitive form holds a prominent position within the winter sport industry, capable of generating over 1.7 billion media views during a winter season. In this domain, computer vision technologies offer promising opportunities for athletes, coaches, and spectators to analyze and understand the skiing performance without relying on wearable sensors. However, despite the many possibilities arising for exploitation, the research and development of computer vision algorithms for skiing performance understanding has been limited compared to other sports such as soccer, basketball, or ice hockey. This is in part due to the lack of public video datasets regarding skiing, that consequently limited the availability of studies with extended practical validity. In our paper, we try to fill such gaps by describing and releasing SkiTB, a new video dataset for computer vision tasks on skiing. In SkiTB, videos capture the performance of the athletes completely from its beginning. It has at the top of the course until its end, at the bottom. In the case of alpine skiing, for example, such starting and stop points often coincide with the top of the mountain and the bottom of the valley. Skiing disciplines offer particular video settings in the realm of outdoor sports. Indeed, the playing field usually spans several hundred meters, if not kilometers, on the mountain surface. This condition requires the placement of multiple cameras along the course to capture the full athletic performance, which in turn gives birth to a video stream with shortcuts. Moreover, as an outdoor winter activity, skiing can be performed under challenging weather conditions, which influence the image conditions, like the presence of the sun causing extreme shadowing, clouds causing flat light conditions, and harsh weather conditions which cause degraded video frames. We designed the SkiTB dataset with three major principles in mind: scale, diversity, and representativity. We wanted to provide a dataset that enables the development of deep learning-based methods. We wanted a diverse dataset such as the algorithms can be developed and tested under different generalization conditions. And finally, we aimed for a dataset that represents well the situations happening in real-world applications. Regarding the scale, here you can see the numbers in comparison with the currently available datasets for skiing applications. Our dataset provides 300 multi-camera videos, from which 2019 single-camera clips are extracted. In total, we provide more than 352K frames, and as can be noted by the chart, SkiTB is way larger than the previous datasets. We aim for the diversity of the data on different aspects. First, we represented evenly three different disciplines: alpine skiing, ski jumping, and freestyle skiing. For each of these three major disciplines, we represented well all the popular sub-disciplines, and we also aim to maximize diversity in terms of athletes represented and course location, spanning all the countries in which winter sports are majorly popular. SkiTB provides labels for all the items previously described. Videos are labeled with the disciplines and sub-disciplines, the athletes' IDs, the location, as well as the weather condition. For the study of specific computer vision tasks, we also provide annotations that describe the visual variability of videos and frames. In addition to the per video annotation, we provide per frame annotations in the form of bounding boxes with occlusion levels and in terms of the ID of the cameras which captured the frame. We exploited these annotations to study the task of visual object tracking. We used the first bounding box of each video to initialize a tracking algorithm that is subsequently run in each of the frames of the video to provide the per-frame localization of a target skier. Obtaining continuous and accurate skier localization is preemptive for downstream higher-level performance analysis. We use the standard long-term tracking protocols and metrics to assess the accuracy of several state-of-the-art methods. We selected the most popular methodologies for generic object long-term and short-term tracking, and we developed 3 skier-specific trackers based on deep models fine-tuned on the train splits we provided in SkiTP. In particular, we released a new baseline algorithm called Stark Ski. This algorithm combines 2 fine-tuned instances of Stark to track effectively in between single camera periods and to cope with the occlusions and camera switches that characterize the problem. About the results, among generic object trackers, Stark results the best. Its performance is comparable to the one achieved on traditional long-term benchmark datasets. These results indicate that generic object trackers struggle to generalize to the application settings represented by SkiTP. On the other hand, skier-specific trackers perform significantly better, with Stark FT improving Stark's F-score by 40%. Comparing the previous findings with the results obtained for the single-camera setting, we observed that camera shortcuts introduce challenges that adversely affect tracking performance. Nevertheless, we can say that skier-specific trackers show promising performance for application, especially in videos acquired by the same camera. By analyzing the F-score per visual attribute, we noticed that the small size, the full occlusion, and the fast motion of skiers are the conditions that determine a performance drop. Camera motion, the scale change, and the background clutter consist in situations better addressed by the trackers. Trackers work generally at the same accuracy level under different weather conditions. These outcomes demonstrate that such methodologies can be used reliably under challenging image conditions. We also performed experiments by training and testing StarkFT on different data splits. The obtained results indicate that generalizing to unseen athletes is the most challenging application case. Generalizing to skin performances occurring after the training ones also proves to be a demanding application condition. Unseen courses instead pose fewer difficulties for generalization. Finally, we present the impact of the trackers on the 2D skier pose estimation task, where pose detectors are run on the frame patches extracted from the tracker's skier localizations. Generally, we observe that employing skier-specific trackers improve the skier tracking results as well as the pose estimation results. For all the details about our work, please refer to our paper. To download SkiTP and the relative resources, you can follow this QR code. Thanks for your attention.